So, yes, I travel a lot between different conferences, and I like to learn the local language at least a little bit. So I get super excited when I learn super stupid things in different languages. Recently I learned a thing, so I'm not sure who here is German, who does speak German at least a little bit. So you know this thing like piep, 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 wir haben uns alle lieb, guten Appetit, right? The thing that we do with kids when we're having lunch or dinner. It exists in other cultures as well. For instance, in Russia, I learned it for a weird reason. It's gusi gusi ga 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 yestratice da da da, and I got very I got very excited about knowing that. And the problem is you can't really work that into normal conversations, which does not stop me from doing it. So here's a bit of conversation that you can actually work into your German if you're not speaking German. Wer ist denn das? If you like see someone like a unicorn, for instance, or a hedgehog or something, and you're like, wer ist denn das? You're asking who that is. Who am I? I'm Martin Splitt. I'm from Zurich in the wonderful country of Switzerland. Switzerland has many good sides. Our flag is a big plus as well. And good that people got it. And I'm a very serious person, as you might tell. This is my LinkedIn profile picture. I highly recommend doing things like that because the recruiter spam goes down. I'm not sure why. I'm missing statistical data. I'm also the head of engineering at a small company called Archaeologic. We are doing like 3D editing in the browser and web VR and stuff. So if you're into that one, chat me up later. And I also am in the Google Developer Experts program, so if you have any questions regarding web technologies, I'm happy to help. And if I can't help, I'm happy to put you in contact with the right people at Google or Mozilla or the W3C or the WG or whatever there is. We have released a thing called 3D.io, which is a platform that lets you build 3D content on the web easier. Boring stuff. Let's go into the more interesting things. Today I'm here to talk about pixels. Oh yeah, and I'm not meaning the Google phones, by the way. Just, you know, making sure it's not, no. All right. No, so we are going to talk about how the browser brings pixels to the screen, which we usually call rendering. And in particular, we look at what means when we're having something that is performant in rendering and what is not so performant in rendering, and why there's differences in these two different things. And for that, we're going to look at how HTML and CSS is parsed, how we are painting pixels on the screen, and what this compositing is that you might have read in articles and seen in video series about. And then we're going to do a little bit of a real-world example, and then we have a quiz where you can win nothing. Eternal fame, maybe. It may be eternal fame. You get your 5 minutes of fame, maybe a selfie with, I don't know, I don't give a shit, whatever. And then if I have the time, I might go over WebGL and Canvas 2D performance in particular. So let's start with pixels. So here we have our little friend who's called Pixie. Pixie is sleeping right now. I had lunch. All the energy levels are drained. So no red lights, no green lights, no blue lights coming from it. It's black and it's boring. However, we can wake it up and go, hey, be green and blue at the same time, and turn them on fully. And then we have this cyan-colored pixel. And then we can change it around and can say, hey, turn it down a bit, but bring the red up a bit, and then we have gray. So all we do is we're describing Pixie in terms of 3 values. How bright the red bit is, how bright the green bit is, and how bright the blue bit is, the blue lights, if you want to tell them. And we have lots of little pixies on our screen. So Pixie isn't alone, that's really good. So here we have a bunch of pixies, and we tell some of them to turn yellow, and some of them to turn blue, and some of them to turn red, and then we paint a face on the screen. That's very nice. So Pixie has a lot of friends, and when they're, turning up their lights, like I just did in the beginning of the, actually I have more lights that I can turn on, I figured. Actually, I turned them on already. All right, I'm probably going to turn them off because it's going to be distracting as hell. And that's more or less what we're going to look at, how that kind of works when the browser does it. So because here we are not actually turning that much on, I made that GIF and now it does itself, but how do we do it when we do web development? And the first part of that journey is the DOM and the CSS OM, or OM, CSS, probably people who speak Slavic languages can actually pronounce that better. Because they can deal with with words that have less vowels than we usually have. And how does that start? This journey starts with a piece of text. as you all hopefully know. So we start writing a bit of HTML, and then we get that as it comes from the network. So the network gives us an HTML tag, and the browser goes, so I have a document, I guess, which is an HTML document. It's not an image or something else. This is an HTML document. And then I have a body in that document. All right, OK. Oh, look at that. There's some text and an H1 element. And oh, we also have an image. We have to download that in the background, and then it's going to paint something on the screen as well. So now we know what we've got. But we have no idea how large it's going to be, or what color it's going to be, or how much space it's going to take, and it might actually change how much space it takes when JavaScript comes in and all that. But we at least know that. But the next thing is we have to figure out how large bits and pieces are. Because when we want to turn our pixels, when we want to go to our Pixies and say, hey, Pixie, you go green, you go red, you go blue, whatever, you go black, you go magenta, then we have to figure out how many of the Pixies we have to have. So that's the first step. Then we also have to figure out if we have a bunch of Pixies that represent our screen, right? We have to figure out to whom we are talking, because we're not going to talk to all of them. So if we look at this screen, a lot of the Pixies are just sleeping right now. A few of them are cyan colored, a few of them are gray, a few of them are white, some of them are yellow. But we have to figure out which of them we have to wake up and give them a color. And we do that using the tree that we just created. We have this the DOM tree, and we kind of, when we encounter the CSS, I'm not having as many slides for that. So basically, the CSS does the same thing. It goes like, okay, this H1 is green, this H1 is this size, and all that kind of stuff, and it kind of like builds a separate tree for the styling. All right, and then this happens in the browser. This is called the layout process. So as these elements arrive, it goes, okay, and this one is, okay, hello world is this size, and okay, and then this goes here, and oh shit, I don't have, shit is a technical term, by the way. I don't have enough space here, so I'm going to put it here, and then comes this image, and it's like this size, and okay, So we have to move around these boxes. But I don't know about you, but if I open my browser, I don't see that. So that happens relatively fast, but you see it's a lot of work, so it's not for free, right? This has to, take some time on the CPU to actually make that happen. So now we know what we've got, and where it goes on our window, and how it's going to look like, in terms of how large it is, right? But we haven't figured out which Pixies to actually talk to and make them in different colors. And this process is called painting. So when we paint, what we are basically doing is we're looking at our screen as a huge list. And basically, this list is like a list of the Pixies that we've got sitting on screen. The pixels, Pixies, whatever. And each of these, we have to, remember 3 values: the red, the green, and the blue value that we want the Pixie to turn to. All right. And basically, when we paint, what we do is we write different numbers in the array. And the Pixies go, oh, I have a new, all right, okay, green. Or in this case, unicorn, if it's me being the Pixie. And what we then create is we basically create a rectangular area of colors, or numbers, really. And we can create multiple of these. We don't have to do it in one go, right? We don't have to paint the entire screen in one moment. There might be situations where we actually want to just take like smaller portions. We want to take lists out of this larger list and then fill numbers into them instead. Basically, what you create is you create a bunch of image files. So if you have worked with Photoshop or GIMP or whatever is out there, I'm not sure, does Sketch have layers? Probably, yes. I'm not a designer, but I knew that, yeah. So basically, you create a layer. And depending on who you ask, this might be named differently. You might call this not a layer, but a texture if you're more into like 3D graphics. If you're more into 2D games, then it's probably a sprite. You might also just call it image. If I use these terms, they're the same thing. It's just like a bunch of numbers, a smaller bunch of numbers than the pixel, the screen is, and we're going to use that later. In compositing, what we are doing is we are putting these images together to form one larger image. We're going to see why that is a useful technique in a second. So here, for instance, we have 2 things. Imagine that we can move each of these circles individually. Then what we probably want to do is we want to paint one circle and then paint the other circle. And then instead of having to paint them all over again, we just move them around. And when they overlap, we have to somehow figure out how that bit in the middle happens, where the color is different from the outsides. But compositing can do that. But how does compositing do that? So imagine we have these 2 images or layers. We have the background from Nyan Cat, and we have the actual Nyan Cat. how do we combine them? I mean, the Nyan cat moves constantly, so it would be nice to not have to repaint it all the time, right? You know, get all the Pixies in order again. Just move them around a bit. So how that works is we're taking the entire background image, put it all over the place once, and then we figure out where our cat should go, and we put them there, and we keep them in memory, and then we copy them into a different position, and into another different position, and into another different position. So what we're doing is basically we're just like, take these two, copy them onto, whoop, that's why I don't like these things. Copy them onto the screen, and copy them over again, and basically just, you know, do that all over the place, and then we get this wonderful animation. I'm not sure why it starts in the middle, but okay. There we go. And you can sing the Nyan Cat song now, because I'm not gonna do it. Okay, I am. Nyan, 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 and so on and so forth. But how does that actually work? Like copying, okay, sure, I can copy numbers, but we've seen earlier on where we had the two overlapping circles that copying isn't quite cutting it because they change the color on the screen. So how does that work? How can I change the color on the screen? So what happens really is, and that's a very simplified view of the process, is we're having a bunch of images, here it's 2, and we run them through a shader, and then we get the output colors on the screen. Now, I say simplified, but actually, what is a shader? Who here has heard the term shader before? Who here knows what it is? And who here has written one? There we go. All right. So, I was like, okay, I'm telling people the things that they already know. Great, I can just go home and cry myself to sleep. No, I'm not going to do that. So let's have a look at the difference between processors in our computer. Who here knows what a GPU is? Okay, for those who do not raise their hands, it's the graphics processing unit. It's basically, so your CPU, the central processing unit, is kind of the piece of silicon that we tricked into thinking. And the GPU is just another piece of silicon that we tricked into thinking, but it's different in structure. So you can think of the CPU as a mind, a brain, whatever you want to call it. I like to call it a very smart filing clerk because it doesn't really think. What it does is it moves numbers around. That's what it's really doing. The CPU is like one big blob. Now, obviously, or well, not obviously, but modern computers oftentimes have more than one CPU. They have 4, 16, 32, however many you wish. But that gets really expensive really quickly. And you can also have GPUs. And GPUs today have 1,000, 10,000, 20,000 little CPUs. So what would you pick? Well, of course, I take the one that has more brains, right? It's like a zombie thing, like brains to brains, brains. But in this case, there's a bit of a problem here, because even though the GPU has more brains, these brains cannot do everything that this brain can do. So this one brain is actually really good at like predicting the future and stuff, and it can do really complicated problems. Like here it has to, loop through a bunch of iterations, and it reads a value from memory, and it adds like the position where in memory it reads from, and if that is 5, it writes into another memory position a certain value, and then it does stuff, and it kind of predicts what's going to happen next, and does like multiple things, and predicts what's going to happen, and it's going to be really fast about it. And the problem is you can't do that. You can't distribute this kind of work really easily. You can, but it's like complicated, and it's like, I have 2 problems, and I now use multithreading, and now 3 problems I have. If you have ever used multithreading, that was absolutely hilarious. If you have not used multithreading, I'm very glad that you haven't used multithreading. So the problem here is, if we are like, how are we distributing this? If I give like the same task to this core and this core at the same, or this brain and this brain at the same time, then this brain here is going to modify the value that this one is using, and then this one, which one does this? Like this one uses the one before the other one has written the new value, or after the other one has written the new value? How does it know when the other one writes the value? This is complicated. I don't want to think about this. I just had lunch. Leave me alone. So our GPU is not a good idea. Is these like 10,000 cores not a good thing? Well, it is, just for different problems. As it turns out, there's problems like this. Matrix multiplication. Who didn't love matrix multiplication in school, right? If you ever had it. If you ever had it, then if other people didn't have it and they go, oh, Oh, it's that time of the day already. I got to take this call. Your phone is turned off. What? I can't hear you. I'm going into a tunnel. So basically what we're doing here is we're taking like the number that's here and the number that's here and put it here. And then we take the number that's here and the number that's here and so on and so forth. And we do it basically the same operation all over again. And the order doesn't really the order in like which cell and which other cell I take, that makes sense, or that's important. But I could theoretically start here and here, and basically do it in whatever order I want, because the outcome does not depend on which order I'm multiplying them with. What it does depend on is like that I take the right cells. But once I take the right cells, everything is fine. So what I can do is I can say, hey, you, do the first bit. Hey, you, do the second bit, and so on and so forth. So they can do it in parallel, and they are much, much faster in filling out the result table than this wonderful person here over there is. So basically, GPUs are really good for what's called a SIMD, or SIMD problem, single instruction, multiple data. It's the same instruction, but it's different pieces of data that hopefully are independent of each other. Okay, what is such a problem? Well, let's have a look. So here we have 16 pixels. Now, obviously, we have more resolution unless you have a super old, I don't know, Tamagotchi or something. Then you probably have that resolution as the actual resolution. We have a few pixels more, and we have a few cores more, but whatever. This is a good example. So we have like these 16 pixels, and conveniently we have 16 GPU cores, so we can assign each pixel to each of these cores. And then we can give them an order. Now, how do we order a program to do something? As a program, oh God, I already gave the answer. How do we order a computer to do something? We give it a program. So let's give it a program. Let's say, take your x and y coordinate. So 0, 0 here, 3, 3 here. And multiply these with 85 and 85 as a second value, and 0, use 0 as a third value. So you produce 3 values, because that's what our pixels need, 3 values, red, green, and blue. So basically they're now going, all right, and in one go, in parallel, they go ba-doomp. And there we have it. So we have rendered a gradient in one go. The CPU can't really, benefit from that. They're fast, so the 16 pixels, you're not going to see a difference. But try that with a full HD frame at 60 frames per second. Just think about it. It's like full HD, so 1080p. So if I remember correctly, it's like 1920 pixel by 1080 pixels. That's a lot. That's a large number that I can't be bothered to actually figure out. And then we have to basically like fill them in 60 times in 1 second. That gives us 16 milliseconds to do that. And in the browser, because it also has to do like event handling and all that kind of stuff, we have like 10 milliseconds to do that if we want to stay at 60 frames per second. So the CPU goes, oh, okay, oh my God, what? The next frame, no, what? Okay, yeah, sure. And then you're losing frames, and the frame rate goes down, and at some point you have a slideshow. And we don't want that unless you program a slideshow tool. Then it's probably okay. If you program a video game, it's not quite interesting. It's like, what? Just imagine, I don't know, a robot unicorn attack in like 1 frame per second. It's going to be. Oh, jump! Oh, I missed it. It's not going to be fun. So this allows us to actually use an architecture, a CPU or GPU architecture in this case, a core architecture, to actually perform these tasks really fast, which is what we want for rendering. And compositing is just that. Compositing is different functions that we can give to our GPU cores to perform these things fast and parallel. And what it does is it takes a bunch of images, it takes a bunch of values as an input, and then produces one set of 3 numbers or 4 numbers, really, because you can have transparency as well, as the output. And it does so by doing it in the shader. So the shader is a function that we are writing, and this function does not run on the CPU, it runs on the graphics card or on the graphics chipset, which is called this GPU. And the cool thing is, these functions, I mean, we've wrote a random function here, right? This is not a reasonable thing, really. But we can write this code, and there is already code for us that we don't have to write. It's because if you're like, I know HTML and CSS, and that is awesome, because I feel like everyone's only like talking about JavaScript these days. But I think JavaScript is nice and fine, but hi, there's HTML and CSS and it's there, awesome, and you should probably use them when it makes sense, just saying. And they come with blend modes and filters. So you don't have to write a lot of JavaScript to make things slow, to make them fast again. You can just use the blend modes and filters that are already available. And what are these blend modes that you're talking about? Well, these are the 16 blend modes that are available in CSS. So this is a boring one. This is just taking the value and like putting the last value that came into the shader is the value that goes out of the shader, really. But everyone else, like here, this one's multiplying, for instance. So it uses the values to multiply them and then take the result of that. Then there's like more complicated things. There's things that invert colors and all kinds of that stuff. But what they all are basically small functions that take a bunch of colors in and produce one color as the output. That's what a shader does. That's what the blend mode what the blend modes do. It can do another few operations really nicely. Translation, for instance, because you can not only use like colors, you can also give it like positions, and then you can say, actually, the thing that comes from 1,1, don't render that at 1,1, render that at 10,10. And then we have moved it already, right? We have gone from here to there. Very nice. This is called translation in computer graphics terms. Rotation means we are multiplying our position values with a matrix that is a rotation matrix. I'm not going to do that. I'm not going to show you the rotation matrix either, but you can Google it. It's all there if you really have to, or you just use the CSS function rotate. You can also scale, because scale, as it turns out, is just like a multiplication with a single value, and then you just render the same pixel multiple times. That's what scaling is about. You start with one pixel and like make that twice as large, then just like render 2 by 2 pixels. Hey, there we go. And they can do blend and filter. As I said, we just use a different function for blending. Filters are slightly different. They use one result color and then change that result color. Also be careful when I say this is a composite-only operation. Not for all browsers. I leave it up to you to figure out which ones are the latecomers. It's a blue one and a Compositing one that are a bit behind. Sorry to say that, but they're getting there. It's going to happen. Firefox shipped Quantum and Stylo, so wow, that's going to be great. Because Firefox was amongst the browsers that did not have accelerate or composite-only filters. And this is how an actual shader looks like. Surprise, surprise, it's not written in JavaScript. Whoops. This is written in a language called GLSlang or GLSL if you want to spell it out. And let's walk quickly through it. So we start with 2 variables. Here, we have types here. I'm sorry for that as well. So we have a vector2. So it's basically a list of 2 elements, an x and a y coordinate. This is why I call them coordinate. And the sampler2d is a way to get the pixel colors out of an image, and we call that image. All right. Then we have our main function that reads the color. So the 3 values. This is actually the 4 values because it can have transparency as well. So this is like an array with 4 items. So red, green, blue, and alpha, which is the transparency. It takes it from the coordinates that we are given on the image that we are given. And then it creates a new variable called grayscale. That's just a single number. And we take the red, green, and blue from the color that we read from the image. And we divide it by, like we sum them up, and then we divide them by 3. So we get the average. All right. And then we use that as the output. And we use that value for red, green, and blue. And for alpha, we say do not make any transparency here. So what this does is, it's a grayscale filter. So if you are saying grayscale this thing, what you're doing is you're going through all the pixels, taking the average of the red, green, and blue, and then put that as red, green, and blue. And then we have the same value for red, green, and blue. And as we saw earlier, Pixie then turns gray. So this is what the grayscale filter does. So if you say like CSS filter grayscale, that's what happens in the background. It runs this program on the GPU, which is half the truth. As it turns out, filters are not necessarily filters, and browsers are not necessarily the same all over the place. And as it turns out, I was talking to someone, I forgot who I was talking with, that said, hey, CSS filters and SVG filters should be the same thing, right? And I'm like, yeah, I mean, they're doing the same thing, really. OK, let's have a look. So you know that in the DevTools, in Firefox and Chrome, and also in Safari and probably Edge, I'm not really using Edge that much, you can enable pane direct flashing. And it gives you a green flash or a colorful flash whenever pixels have been repainted. And pixels repainting is slow because we have to set up all the numbers in the array again. So this is a CSS blur filter. No green rectangle. That's pretty good. And this is an SVG filter. Oh. Oh. So they are not the same. And honestly, I think the blur should actually, if I'm not stupid, and I talked to a few people who agreed with me that I'm stupid, I mean not stupid. I'm in a unicorn onesie. I'm like, I'm stupid. I mean, who would do that? No, actually, it's like really, really fluffy and nice. But the lights are pretty warm as well, so that's not necessarily a smart idea. And I think blur actually I think this is a bug in the DevTools actually, because blur is a post-processing effect and it has to do it in 2 runs. So I don't think this is actually representing the truth. Nonetheless, SVG filters do behave differently in terms of compositing for historical reasons. There's a bug in Chrome open to fix that. I would love to see that in other browsers as well. I have talked to people from different browser engines with different results, but I think if the community talks to them as well, they might, think that maybe we should have a look at that. I know that SVG is actually really tricky because it's a relatively old technology, but I think we should make it fast because it's an awesome technology. Moving swiftly on, I go on a tangent here. So let's have a look at a real-world example, because all this was really abstract so far. So let's have a look at this thing here. This is a travel companion. It has a drawer menu, which is UX-wise not a good idea, but everyone does it nonetheless. So here we have it coming in, and then it slides out again, and it's the best app probably ever written. Now let's have a look at how that looks. Okay, so we have a list that is our menu, and then we move that menu over to -200. It's absolutely positioned, and then we transition. We say that if we change the left property, we want to transition it. Okay, cool. And then once we are having it, active, we are moving it to left 0. So that's how this animation comes to be. All right. This is what the DevTools timeline says. And oops, you might see, so we want to see like a straight line here of 60 frames. We're not quite there. And you see the work, this is all green. And if you remember the green rect flashing, that was painting. So we are painting all the time. And let's have a look at that with the, oh, wow, right? So this is paint rect flashing in Firefox. So every time it is painted, it changes the color. So it paints a bit, right? This is paint-orama, or how I like to call it, my clicker died. Repaint disco. It's like repainting all over the place. And that's because of this pipeline. So okay, this is like the pipeline. JavaScript changes something in the styles, then maybe we have to run layout, maybe we have to run paint, and maybe we have to run we have to run composite in the end. Now layout does not happen because we positioned it absolute, so it does not move other things around, so we are skipping that step. That's good, because less work is good. But can we do better than that? Yes. So here I changed the code slightly. What I'm doing is I do a translate 3D -200 pixels. So we are also moving it 200 pixels out of the screen to the left. But we are doing it with a 3D transform. And then whenever we are looking at it again, this looks better. And actually, I think it shouldn't repaint, honestly. But for some reason, it does in Firefox that I'm using there. But at least we're not having the repaint disco. And it makes sense, because now we have said, hey, this is a separate image. And I just want to move it around. And that's what the shader can do. I do not have to repaint all the pixels. I just move it in the shader. And look at that. Sailing smoothly, and nothing happens here. That's really good. So that was before. That's after. Very good. So we skipped the paint step mostly entirely. In Chrome, it was skipped entirely. In Firefox, it was painting, unfortunately. And Paul Lewis, before leaving the DevRel team of Chrome, unfortunately. Hi, Paul. Please come back. Anyway, he said, performance is the art of avoiding work, which is what I said to my boss on the performance review. And yeah. No, that was fine. He is like, quoting Paul Lewis, I see. No, he wasn't. He was staring me down, and I'm like, I'm sorry. No, just kidding. My colleagues are actually really nice people, and we are not hiring, actually. Are we hiring right now? I'm not sure. So let's have a little quiz real quick. Let's play a game. Assuming that we have an element, and we're having a translate x 0 applied, and after 2 seconds, we use JavaScript to make that to a translate x 200 pixels. Will it paint? Raise your hand if you think it paints. A few people, all right. Dun, dun, dun. What? It painted? Oh my God. Martin lied to us. He said it's composite. So why is it not compositing? Well, that's because I haven't told you the full truth just yet. So actually what it turns out to be is, so I said something about it needs different images to have the compositing, right? If I have one big image, I can't do composite with it because I have one gigantic image. I can just move that image into the screen and that's pretty much it. So if I have things that are moving against each other, so the thing hopping around, for instance, I have to have multiple images. But if you think about a normal website, like Facebook or Twitter or your company website maybe, you have a lot of elements there, like the H1s and the images and the buttons and all the list items, all the postings, all that stuff is there. So having an image is actually pretty expensive in that case, because if you would make each of these elements an image, you have to basically put it somewhere in memory. So you're consuming more memory just to have a representation of it there. You also have to consume more memory because you have to have a list of all the things that you need to put into your compositor. And then the compositor has to composite more images, so it's also slower. So if you have 5,000 elements that are all composited, then that's not going to be super fast necessarily, depending on what kind of compositor shader you're running. So in order to reduce this cost, the browser goes, normally websites don't move around all over the place, right? So Facebook, when I scroll, does not go like, whoa, right? Would be weird. So basically, the browser looks at hints for layer creation. It tries to be smart about it. And one hint is if it's a video element or a canvas element, because they're changing a lot of times, so it makes sense to manage them in a different piece of memory to begin with. Fair enough. Also, if there's a 3D transform, translate X is not a 3D transform, it's not working, so it has historical reasons, don't get me into that one. Basically, if it's a 2D transform, it goes, nah, it's fine, it's not gonna be like super complicated, so I'll do it like once or twice and then I'll be good. Right? And that's mostly true, but not always. That's why the translate Z hack works. If you say translate Z0, you do not do anything, but you tell the browser 3D transform, Z axis, and the browser goes, all right, layer it is. Layer away. Also keyframe animations, no matter what kind of transformations they are, as long as the keyframe animation can be done in composite only. So if you're changing the color in a keyframe animation, bad idea, because you have to repaint the pixels then, because you have to get the new color there, right? But if you're just moving things around in a keyframe animation, no matter how, that's usually, or that in most browsers is then composited and actually not repainting. Then there's the will change property, which will not automatically create a layer, but it will give the browser a hint to look at certain properties. And if they are changing, it might create a layer if it thinks it makes sense. Okay, another try. Slightly different code. Dim 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 dim. Will it paint? Will it paint? Oh, people are this. Okay, okay, we have brave people going, it will paint because I say so. It doesn't. It does not paint, I'm sorry. And that's because it was a 3D transform. If you look at it, it was a translate 3D. Even though we are actually only translating on one axis, it is the translate 3D, and the 3D transform makes it composite only. Okay, cool, that was good. Another one. Slightly different code. Dim 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 dim. I am running over my time slot. I'm sorry. Will it paint? Will it paint? And I learned another thing from the Russian language. The Russian languages has this. So Germans have that as well. Since 1996, we have Jein. I'm old. Okay, fine. Wow, no one's going for that one. Okay, fine. The Russians say da, niet, navernaye, which means yes, no, maybe. And that was the answer that I was basically getting from you. And it does not paint. Because it is a translate, it is a 2D translate, but it is in an animation. So it goes, look at that, I can make that into a composite action, and then here we go, smooth and no green rectangle of sadness. I'll skip that part real quick. I know it's sad and stuff, and we have a challenge. We draw an image on multiple spaces and stuff, blah blah blah. This is the WebGL code for it. That's a small part of the WebGL code for it. This is the other small part of the WebGL code, and it's still not complete. So this and this together render a triangle. I think in terms of code complexity, Canvas 2D wins. How are we doing in terms of frames per second? So here, on the x-axis, we have the amount of images that we are rendering at the different random size. So we have an image of one size, and we are rendering it 100 times, 250 times, and so on and so forth, in different random sizes. And this is the frame rate. Is 60 frames per second is here. So this is good. This is meh. And this is, oh God, no. And as you can see, once we hit 500 images in Canvas 2D, not so good. But how's WebGL doing? I mean, it's a lot more code, right? We have to make so much more code, so it's going to be faster because it's using shaders. So Canvas 2D cannot really use shaders nicely. There is accelerated Canvas 2D, which is doing a bit better, but it's still not like quite there. So if we use the accelerated Canvas 2D, so here's the accelerated Canvas 2D, here's WebGL, and we run it with 10,000 objects and 50,000 objects. I mean, here it is a slideshow, right? So yeah, So we kind of like get there. So Canvas 2D, while having easier vanilla code, it does not have as much access to the shaders and as much access to the pipeline. And for WebGL, there's libraries available. WebGL is not supported everywhere. If you have a potato and run an old version of Firefox, it's a bit tricky. Or if you order an old version of Internet Explorer 6, probably not that good. So WebGL, all the things because they're fast, God, no. And people still come to me and say, like, so I want to write this library that does this thing all in the canvas. I'm like, no, don't. Because it's not the right thing. The web is so powerful because HTML and CSS give you a lot of things for free. Even though you might think they're terrible and slow, and they're actually quite lively. And they give you semantic and accessible content. It's accessible to screen readers. You already have UI primitives such as sliders and buttons and drop-downs and all that kind of stuff. You would have to rebuild all that. And SVG gives you possibilities to have like responsive graphics and animations, and you can declare them, and it's really nice. And Canvas 2D is pretty cool for like simple two-dimensional stuff. But for more complex things, even in 2D, where you actually can benefit from having your own shader code, that's where WebGL shines. You should not try to do like UI primitives and semantic and accessible content in WebGL because you have to rebuild everything. Everything. Because to the browser, it's just a huge array of pixels, and it doesn't know anything. It has no meaning. Also, a quick important message. Last call for Mr. Flaki. You should get a Nintendo Switch, I was told. If you prefer CSS, that's right there. Thanks to custom properties, I can do that as well. All right, that was it. Thank you very, very much. Slides will be online in a second.